Hello all, we've got the second homework of computational method and let's see what's there in the homework. So I've already opened up this. So here it's given generate a surface coordinates of an helical pipe having an elliptical cross section with a major and minor radii of 1 and zero point 0.5 respectively with a central helical curve defined by the following parameterization in T starting from 0 to 6 pi. Okay, so let me simplify the question for you. So it goes like, so the question asked us, let me draw a, let me draw you in coordinates, x and y coordinates. It's better if you could draw z coordinates as well because we'll be talking in 3D. Let's draw it like this. Okay. So the question is asking us to draw an helix. For example, something like this. Obviously, it will be in 3D. Now we have to, you know, plot, draw ellipses on the curve like this, which will follow all along the curve from the starting point to the end point, from the bottom to all the way to the top. Okay, so this is the task for today's homework, and the major and minor radii of 1 and zero point 0.5 means the radius of the radii of the helix would be 1 and zero point 0.5 like this, and uh, the parameterization points are starting from 0 to 6 pi. Okay, so let's go to the part 1. So it's saying using a closure. So closure is a concept from computer science, which I'm going to explain while defining this function, while doing this code. So using closure, explain and code a higher order function that returns a function. Calculate the Frenes array of t dr by ds means the tangent function and a normal function. Okay, obviously they are vectors of the helical curve. So before starting this, let's draw a curve. Okay, let me make a new notebook over here. Let's name it as helix homework 2. Okay, helix homework 2 or helix homework you can write. Anyway, so first and foremost thing we're going to do. So firstly, I'm going to make a function which is going to draw a helix. Okay, first we draw the helix and then we'll go to the Frenes array function, how it works. We'll need to talk about what Frenes array. Okay, so first and foremost, we're going to import uh, numpy as np. Otherwise, we're going to use jax. So I'll tell what jax is. So let's import numpy only as beginning by as np. Then we need to plot labs. So import plotly. Okay, let's import from plotly dot subplots import make subplots. Then what we need? We need to import jax. I'll tell what jax is, but for now it's not required. Let's make it a bit simpler only. These two things we need. Okay, there is an error as mp What is there over here? Plotly dot subplots. Some typo is there. Port make subplots. Okay. I forgot that underscore. That's why you're getting there. Anyways, so it's fine. So let's define this function of helix. Let's call it helix only. So it has three parameters: t, then radius of the helix, then mg. So I'll tell you what t, r, and mg is over here. So t is how far you're going along this curve. Okay, how point for example t is 0. So let me draw you and tell you how what is t. Let me erase this first. You don't need this what do you call coordinates for now. Let's draw in simple helix first. Okay, so over here e means it starts from point 0. Okay, this is if t equal to 0, it is here. T equal to 0, t equal to 1, it will move to here. T equal to 2, it will move to here. Like this, well, t equal 10, we're going to reach the end point. Okay, and r is the radius. Okay, radius of the helix, and then mg means see after every point it's moving up. It's x, y, and g. So after for mg you can take something like 1 by 2 pi. Okay, t by 2 pi you can say. So if it moves along the t, so after every turn, how far it is going to move in the g directions. Okay, so this is the g direction. You can take this as x and y. So after each turn for one revolution, how far it is going to move in the g direction. So this is the concept pitch of the helix. Okay, so how far it is going to move in the g direction after each revolution. Okay, each revolution of 2 pi. So this is defined as mg. Okay, so we've taken here we have taken 1 by 2 pi. We're going to change that if it's required. So I hope you understand this. So this function we have taken like this. So it will return np dot you know cos t minus np comma take function take the argument p, then np sin t, and then the no, the parameter p. Okay, so how far the pitch actually. So let's multiply r, so we'll get it definite defined radius, and as I said t into mg. Okay, so now I have to define the value of r and g. R is equal to, let's take something like 7, or you can make it even smaller. Let's make it as 4 or something. 3 or 4, let's take 4. Mg, as I said, it will be 1 by 2 pi. Okay, so cannot get any error, so it's fine. So let's take uh, any value of e and we'll see what we are getting. We should be getting 3 points in the space. So let's take t as uh, something like pi by 4. Okay, and rg value already given, already defined. What if I give it again? So this is the value of the helix. So at this point, np means at pi by 4. So we got three values. So we're able to define the points at this in the space for this helix. Okay. So now we just have to change the values of t. So for example, this is the point called n pi, n pi by 4. Okay. I mean pi by 4, pi by 4. So at this point, you got three values, three coordinates of this point, x, y, and z. So we're able to define this point by just giving the value of t, as we have already defined the value of r and mg. So now what you can do, let's take some values of t and plot in helix. T is equal to np dot linspace. We're taking some values, linspace, as given in the question, 6 pi will take. Let's take around 200 points along the helix. Like we'll take 200 points starting from 0 to 200. So t is over here 200. Okay, we can change that later if required. Then we'll put the value of t in the helix function. So t, we have already defined the value of r and mg. So you can see we have got several values. Let's unpack them into x, y, and g. X, comma, y, comma, g. So we'll unpack all the values into x, y, and g. We have successfully unpacked them. Let's plot it down. Figure is equal to make set plots. Fig x equal to x, y equal to y, g equal to g. Then mode is lines. Okay, let's see how it turns out. Okay, did I made some mistakes over here? Figure is not callable. Why? Okay, sorry, I forgot this. Fig dot add scatter 3D. We are doing a 3D plot. So okay, so as you can see, you got our helix. Okay, this is our helix. So now what we'll do, we're going to plot. So this is the thing. Till now, till this point, everything is clear, I believe. So we have plotted successfully a helix. Now we're going to plot the ellipses. Okay, before plotting the ellipses, I need to take you through what is a Frenes array. Okay, what is a Frenes array and why you will going to use this over here. So basically, Frenes array is an very fascinating function. What it does, let me tell you. Okay, let me erase all these things. Now let me scroll down. Okay, so okay, Frenes array, Frenes array function, which will calculate. So basically, it will take a function, it will take one function and then return two functions. Okay, in turns. Okay, so we're going to calculate what are the functions and why we need these functions. Okay, so Frenes array. So what is Frenes array functions? Okay, so it is nothing but it's for example, just take any curve, some curve like this. Okay, so you take derivative of this curve with respect to no, any parameter over here. For example, this is something like y is equal to x squared, x cube, or plus 2x or something. Okay, we'll take with respect to derivative one time. We'll get definitely going to get a tangent function. Let me do it properly. It's not properly perpendicular. So it will look like something like this. To take derivative with respect to one. This is the tangent. Okay. So what Fanisera does, what it will do, so it will give proper tangent function. which is defined by, we'll get the proper magnitude of the debt, like it will be like the function, we'll take the derivative of the function divided by magnitude of that function, or you can say the normalized function of the function. Okay, so it will give us the tangent. Okay, to find the normal, which will be perpendicular to the tangent, and which will normally, if this is the curve, this is the tangent function. If you see, so normal will be perpendicular to the helix, to the what you call, to the tangent. So this is the normal function. Get the normal function. What is the formula for that? The formulas are provided by the Fresnel series. Okay. So it's same, but we'll to take the derivative of the tangent, then the normal of the tangent. Okay, this is the function, just any function. Okay, so we got tangent and normal from the curve. Okay, which are perpendicular to each other. And let me tell you why I'm talking these things, why you're going to calculate tangent, normals, and all these things. We're able to calculate the ellipses. What is the relation between these two? So basic concept is we need to take a point on the helix where you can calculate two vectors. This is the vector, this is another vector. We need another base vector which will be perpendicular to these two. Okay, perpendicular to these two. Okay, some base vector. And how we going to calculate a vector which is perpendicular to another vector? It is simple, like just take the cross product of these two vectors. So we'll get another vector. Now you see we got two vectors which are perpendicular to each other. And what we're going to do, we're going to use these two vectors to make our ellipse. So the defined radii is given. So we'll just take some kind of radii and put this function. So using these two vectors, you can easily going to plot this ellipse. And as you're going to change the value of t over here, for example, that t is something like, let's take pi by 8 or something. Okay. So if we change the value of t, we'll be able to calculate various ellipses along the path of the helix. Okay. And that's what we wanted. And see, the entire process is simpler because of the Fresnel series function. So over here, we're going to define a function what will take one function and give two function in returns. Which two functions? In our case, it's tangent and normal. Okay. So let's delete these things. These things are not needed now. Just to explain you guys, this thing. Okay, so we have defined our helix function. Now let's define our Fresnel function. Fresnel function, which will take one function. For example, let's take f in our case. Okay, so what it will do, as I told you, you have to take derivative of this function with respect to an argument. And what in our case, this was in this case, we just taken an example. I've taken this, we have y is equal to x cube plus 2x, some any function. But in our case, the function is helix. So this function is helix in our case. So let's take the derivative of this helix df dt and calculate the derivative. We don't have to write a code by own ourselves. There is another no what you call uh, an a feature called JAX. They're developed by Google, and JAX what we're going to do, it will automatically write the code to calculate the derivative. You just need to import that. So we'll go to import JAX, then we're going to from JAX dot numpy, will import, or you can say like import JAX dot numpy as JNP. Okay, okay, that's done. So we're going to use a beautiful function called Jacobian. What it will do, Jacobian going to calculate it will going to write its own code to calculate the derivative of any function. For example, we're going to calculate the function, calculate the derivative of the helix function. For example, now in this case, we're going to pass the helix function to this Furness array as f. So we have to write this code as df dt means derivative of f. So we're going to write jx dot Jacobian will pass this function f. Okay, so pass this function f, and yeah, so pass this function f. Now let's define our two other functions, which are tangent at some point t. You have to calculate. Now we need to calculate the derivative of that function, means the derivative of f function at some particular time, which is at some particular point on the helix. Here it is t. So let's calculate the value of df dt at t. Okay, and let's store it as df dt result. Okay, I've stored this, and as I've told, and this would tangent function, what it will go, it's going to give a function. And how are we going to calculate the tangent function? We've taken the derivative already. We'll have to divide it by the normal of this function, normalization of this function, or you can say magnitude of this function, or it's a vector as well. Okay. So over here, what we'll do, it will going to return df dt result divided by, as I said, you have to divide by the normalization of this function. So to calculate the normalize, there is a predefined function over here, jnp dot lineals dot norm, and we'll just put dft results. Okay, so the tangent function will return, no, this value means the exact tangent value according to the Furness array. So let's see it's right or not. Okay, it's absolutely fine. Let's define another function, our normal function. And to get the normal function, as I've told, we need to calculate the derivative of the tangent. Okay, so let's calculate the derivative of the tangent. Let's call it t tangent. T tangent t2 is equal to Jax dot Jacobian. Will pass the tangent function over here. Okay, so it will going to calculate the Jacobian of the tangent function, or you can say derivative of the tangent function. Then let's define our normal function, takes argument t, and let's store it the value of Jacobian of the tangent function at a point t. So let's store it in t tangent dt result. What it will do, it will going to you know calculate the tangent function at a particular value of t. Okay, and what it will going to return, it will going to return the same thing as that, but here I've already calculated the derivative or Jacobian of the tangent function divided by the norm of the tangent function. Okay, so to calculate this, you'll go to d tangent divided by jnp dot ln dot norm. Then we're going to calculate the norm of this tangent, Jacobian of the tangent at t. So I've calculated this. Okay, okay, okay. Now it should be fine. Yeah, and to calculate these two functions. Now the what we're going to the Furness array function is going to return two functions which are tangent and normal. Okay, it should be inside this. Ah, now it should run. Okay, so let's see what it returns. Let's pass an argument. Furness array. Let's pass this helix function. At t you have to define because t value you haven't given. Let's take t is equal to np dot pi by 3 or something to give the value of r and ng as well. Okay, so we're getting error. Let's see what is the error over here. Let's call it again. Friend sharing. Let's give this function helix the value of np dot pi comma r comma ng. It should be fine. Why it's giving error? Then maybe you have to get values of, or okay, let's see if it'll give. Okay, we're giving delete value. That's why it's giving error. Let's put t and define the value of t over here. We'll see. T is equal to np dot pi by 6 pi by 8 or something. Still you are getting error. Okay, it should return friendly array. What's the error over here? Let's see what's the error over here. It's fine. Friendly array will put helix the function. Okay, it's giving error. Okay, it's fine now. Already defined the value of t, so can't pass the parameter. So it's fine now. It's no giving no error. So another thing I need to discuss over here. See, the value of r and t, r and g, mg I've already defined, and the function which I've given over here is the helix. So as the helix has three parameters or three arguments, this function will also going to take three arguments. But I don't want to give these arguments r and g into this Fairness array. So what I'm going to do, I'm going to fix the value of r and g. You can say as a default arguments. We're going to fix these values, and for that, I'm going to introduce a new thing called partial. Partial is another beautiful thing. What it is going to do, it is going to make any function as partial by fixing uh, no the unrequired arguments like r and g over here in the case of helix. You're going to fix the values of r and g by making it partial, and you're going to vary the value of t because you just need to vary the value of t as r and g are already defined. So let's call this function partial. Before that, you need to import this import functools from functools actually from functools import partial. Okay, so let's take the partial function. Partial will pass the helix, then we'll fix the arguments. T is equal to, no, t is going to give the values. R is equal to r, this r, then mg is equal to mg. Okay, so first argument, what's the error now? Partial helix we passed. I need to fix these arguments. T comma r comma ng. First argument must be callable. I don't know what it means. Let's see. Okay, t value we haven't defined, that's why. Let's take some value of t. T is equal to zero point 0.1 or something. Mm, let's take np dot by and something like that. Okay, why it's giving this error? Partial should not be giving this error. Don't know why. Partial first argument must be callable. Partial, we pass the helix function, make it as in partial. Let's see what partial means. What are the things it needs? Okay, partial self, comma args. With the arguments, we're going to put new function with a partial application of given argument keywords. Okay, partial helix. I'm going to fix this. Okay. Now I got it. I was putting brackets over here. I was putting the wrong syntax. That's why t is equal to t only. Now r is equal to r, mg equal to mg. Now it is going to give. Yeah, that's right. I was putting the wrong syntax. That's why I'm getting the error. Anyways, so we got the partial function. Now what are we going to do? We pass this partial function into a Fennes array. Fennes array, we pass this. So as you can see, as I passed my partial function over here, the helix partial function. So we partialize the helix function by fixing the value of r and c. We're going to change the value of t over here, and we got two values of the vectors, two values, two functions as in return, which is tangent and normal. So let's save them, or you can say unpack them into two arguments or two, variables called tangent and normal. Okay, so it's done. So let's see what we are getting if you're going to pass something like, let's pass some values of, just to check, some values of t. uh T is equal to np dot linspace 0 to 6 pi, the value which was given in the question. Let's take 20 30 values, 30 values of t. So they have, saved in this. So let's see what are the values of tangent. The tangent is the function. Okay, you can't see the function. Got it. To I got it now. Okay, so we've saved the tangent and normal function here, and so I think we covered the part one pretty much over here, like using the closure. Okay, closure. What closure mean? I forgot to talk about that. Over here, you can see what closure means. See, we pass the value of function at t. Okay, some value of t. We pass the function in the in terms of helix. Okay, in the argument of the helix, we pass this over here, and this calculated the values, differentiated, to calculate the Jacobian, and I can see this normal or the tangent, these two functions are retaining the value of t. Okay, even though they are not directly connected. This is called the closure. Like you know the beauty of the computer science, where you pass in value. See over here, you can see that t value is not directly, the function, you know, what you call the properties of the helix were directly not given to the the tangent or normal function. They are passed through directly to this f function to the Frenes array. But the tangent function retains the properties and knows the values of the helix function, the tangent and normal. That's called the closure. Okay, guys. So that's the part one of the homework problem. So we're going to stop over here, and in the next part we're going to uh, explain and code a function that will calculate the surface points of the elliptical section. And I will explain why I was not able, will not able to get points in the tangent, because this is the function. We're going to break this function and form another function which is going to use these two functions to point surfaces on the helix. Okay, so meet you guys in the second part.